Welcome to 4.3, Theory of Polynomial Functions. So again, still working on polynomial functions. We have a theorem here called the conjugate zeros theorem. So if p of x is a polynomial with real coefficients, and a plus bi, a complex number, again, as a reminder, this is the complex number form, is a zero of p of x, then the conjugate, a minus bi, notice the difference is just the sign, must also be a zero of p of x. Example 1. Find a cubic polynomial having zeros -1 and 3 minus I. And then after that, we'll find a polynomial satisfying part A, but also having that p of 1 equals 5. So first off, for part A, we know it's cubic and it needs... What do we know about cubic functions? That again is x cubed, so that means we need 3 linear factors to give us that x cubed when we multiply them together. So I need x minus some value times x minus another value, again, the main setup for the linear factor, and x minus another value. Those 3 x's will end up, when I multiply them together, give me that x cubed for my cubic polynomial. Now, what are the zeros I have? I have one zero, which is -1. So I'll plug that in. And then I have another zero, 3 minus I. What would my other zero be? Well, again, remember, by the conjugate zeros theorem, if we have a minus, then that must mean the positive version is also a zero. So the positive version, 3 plus I, must also be a zero. Okay, and there we go. Let's go ahead and multiply this out to get that polynomial. So that's the linear factors. Let's go ahead and start simplifying this. And then let's see what I would get. I would get x minus 3 plus I times x... Oh, that would be an x minus 3. Okay, and then minus I. Now I want to multiply this out. Oh, notice something real quick. These are the same. These are also the same, and then we just have a difference of signs. So this is the conjugate pair from the difference of squares. So I can easily multiply this out and just square the first term, x minus 3 squared, and then minus the last term squared. That's how I would multiply the conjugate terms. Again, from a squared minus b squared equals a plus b times a minus b. Again, a squared minus b squared factors into those values. So if I see the conjugate values, I know I can multiply them out like that, which is why I squared this term and then squared that term. Okay, and if you need any extra help on factoring the difference of squares, let me know. So factoring this out, that would give me x squared minus 6x plus 9. Again, as a reminder, x minus 3 squared is the same as x minus 3 times x minus 3. And we would use FOIL to multiply that out. Okay, and then minus I squared. Let's see, x plus 1 times, I squared again is -1. Okay, so since I squared is -1, we'll go ahead and replace that with -1. Which means we'll end up with x squared minus 6x plus 10. Okay, and then let's go ahead and just multiply out. We'll go ahead and multiply the x first. And that's going to give me x cubed minus 6x squared plus 10x. And then we'll go ahead and multiply out the 1 to each term. And that will give me plus x squared minus 6x plus 10. Okay, so I can simplify that out to x cubed minus 5x squared minus 6x plus 10. All right, so that's part A. Now, we're going to use our function p of x. And real quick, I want to change this to a -1. That's a small typo there on the lecture notes. Please change that to a p of -1 equals 5. So we want to find a polynomial that'll satisfy p of -1 equals 5. And we're going to use the polynomial here. To do that, we're going to multiply our polynomial by a random variable a. So multiply p of x by a. Then we're going to let x equal -1 because that's what we're trying to input over here. And set a times p of 1 equal to 5. So let's go ahead and do that. Multiply a to my function, and then it's going to be my x cubed. But again, we're inputting -1. Oh, that should have been a -1. Minus 5 times my -1 squared, minus 6 times -1, plus 10. Again, we're just using our generic function here, but we're inputting a specific value of -1 to create a function that'll give me a 5 when I input -1. And again, I want to end up with a 5 when I do this. So let's see, simplifying, I'll get a, that'll be a -1 minus 5 plus 6 plus 10 equals 5. Okay, so then the -5 and the -1 will cancel with the 6, and we're just left with 10. So we have 10a equals 5, and then solving for a, we'll get a equals a half. So now, with that special factor of a half, we create a function that'll specifically give us a 5 when I input a -1. So my function is 1/2, and then x cubed minus 5x squared minus 6x plus 10, which you could multiply out if you wanted to. But again, this specific one will give me -5 when I input, or will give me 5 when I input -1. Now let's move on to example 2. Let's sketch a graph of this function, p of x equals 2x cubed plus x squared minus 7x minus 6, and it gives us the factored form. What is special about the factored form? Well, again, the factored form will give me the zeros. And what is special about the multiplied out form? Well, when it's multiplied out, I can look at that and I can see if the leading coefficient is odd or positive or negative. And then I can also see if the highest degree is even or odd. Oop, that should be odd. So that's the reason, there's special reasons for why we want the multiplied out version or the factored version. So going with the multiplied out version, again, we can find out since it's a positive 2 and our degree is a odd number 3, we know we're going to be looking at a function with the end behavior of this. Now let me actually erase that and write it out a little nicer. So again, we're looking at the end behavior. Because we have a positive 2 coefficient, and then degree 3, we know the end behavior is going to look like this, based off, again, of this form. And then we know we're going to have 3 different zeros based off of our factored form. Our zeros are going to be, let's see, x minus 2, we'll set each factor to 0 to find our zeros, 2x plus 3, and x plus 1. And then we find out that x equals -1, x equals -2 or -3 halves, and x equals 2 are all going to be our zeros. So we can go ahead and plot those points. I'm going to be approximate. Let's say this is -1, +1, 2, and -2. I'm not going to worry about any y values. We're just, again, doing a quick sketch. So I know my graph has the points +2, -1, and -1.5. All right, so I know it has these points. How do I figure out how to graph it? Well, I know the beginning part needs to be going downwards. And since I don't cross any more times over here, I know this first part here is going to be from coming downwards. Okay, so it goes downwards, but then it has to come back and hit the -1, which means it needs to pop back. How high up it goes, I don't know, but again, it's just a sketch. And then once it goes down, I know it needs to go back up and cross the x-axis in order to head up to positive infinity. So at some point it pops back up. Where, again, we don't know. It's just a sketch. And it heads on up. And there we go. We have a rough sketch of our graph. again using the end behavior and then our zeros. So moving on, the rational zeros theorem. So if we have a polynomial p of x and it equals, and we have again that just generic way of writing out our polynomial, then the rational number p divided by q, written in lowest terms, is a possible zero. So again, a possible x-intercept, where p is a factor of a zero and q is a factor of a sub n. So for example 3, list all the possible rational zeros of p equals 8x to the fourth plus 3x cubed minus 7x plus 6. So to find all the possible rational zeros, all I need to do first is to figure out my p and my q value. So p again is the end, and q is the first one. We're going to first write out all the factors of those values. So let's see, p again, as I mentioned, a sub 0 was 6, and my factors are going to be 1, 2, 3, and 6. Those are all the factors of 6. Now for q, again, that's my a sub n, that was 8. And what are my factors? The factors of 8 are 1, 2, 4, and 8. All right, so we've created our factors. And now what we need to do is write the p divided by q options. A few different ways to do this. We also, be careful, have to take into account the positive and negatives of each of these. So positive and negatives of p divided by q. The way I go about this is first I'm just going to focus on 1 from p, and then slowly divide it by each of these factors and write those possible options out. And then after that, I'll move on to 2, 3, and 6. So first off, I have 1 divided by 1, which is just going to be 1. Then I'll do 1 divided by 2, which is a half. Then again, the 1 divided by 4, which is a fourth. And then the 1 divided by 8, which is, again, an eighth. All right, so I did the 1. Now let's go ahead and move on to 2. I'll go ahead and do the same thing, divide it by each of those factors. So let's see, 2 divided by 1 is just going to be 2. Then 2 divided by 2 is 1. Oh, I already wrote down 1, so I don't need to write that again. Then 2 divided by 4 is going to be, that's going to be a half, which I already have. And then 2 divided by 8 is going to be a fourth, which I already have. Okay, so I'm done looking at 2. Let's go ahead and look at 3. Again, 3 divided by 1 is going to give me 3, which I don't have yet. Then 3 divided by 2, which is going to give me 3 over 2, which I also don't have. And then 3 divided by the 4, which is the fourth. And lastly, 3 divided by 8. I don't have either of those, so I'll go ahead and write those down. All right, almost done. Let's take a look at 6. 6 divided by 1 is 6, which we don't have yet. And then 6 divided by 2 is 3, which we already have. 6 divided by 4 is going to be 3 over 2, which again we already have. And then 6 divided by 8 is going to be the 3 over 4, which again we already have. So these are all the possible zeros. Remember, we're talking about the positive and negative options for all of these. So if we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but again, positive and negative, so there's actually 20 different possible zeros for this. That's a lot. So we're going to go look a little later in how to narrow this down. But first, moving on, let's go ahead and look at the fundamental theorem of algebra. So every function divided by a polynomial of degree 1 or more has at least one complex zero. And then the numbers of zeros theorem. A function defined by a polynomial of degree n has at most n distinct different complex zeros. And then real quick, note that real zeros are complex zeros. Now let's take a look at the multiplicity of zeros. What does that mean? Well, real quick, remember if we have f of x equals x minus 1 times x plus 2, we have two different zeros. We have positive 1 and negative 2. But what if my polynomial had factored into x plus 2 times x plus 2? I could rewrite this as x minus 1 times x plus 2 squared. So this one has multiplicity of 2, while as this term has multiplicity of 1. So that's what we're talking about when we're talking about the multiplicity of our zeros. So if we just have a multiplicity of 1, like this example here, we know at that 0, it's just going to cross through it, either up or down. Then, if it has an even multiplicity, like 2, it's going to hit that 0 and then bounce back. Hit the 0 and bounce back when we were graphing this. Last option, let me just throw one in here. If I did, for example, maybe x minus 4 cubed, that one has an odd multiplicity. So when it's an odd multiplicity, it's going to just kind of curve through. All right, so again, these are the examples of the multiplicity. For example 4, we're going to find a polynomial with a 0 of 0 with a multiplicity 3, a 0, 3 of multiplicity 1, and a 0, negative I. All right, and again, by the conjugate theorem, if we have a 0 of negative I, we know we're going to have a 0 of positive I again, as we covered earlier. So let's see, we know p of x is going to equal, well, when we have a 0 of 0 with multiplicity 3, that's just going to be x cubed because x would equal 0. And then let's see, 0, 3 of multiplicity 1, so that's going to be x minus 3 to the 1 power. And then we have a 0, negative I, which I'm assuming is just going to be multiplicity by that self. So it's going to be x minus I, and then again we have to remember the conjugate x plus I. So as a reminder, why the 0 right here is just x equals 3, that'd be just x plus 0, remember, would give me a 0 of 0. All right, so there we go, we have our polynomial. Let's go ahead and multiply it out. So that'll be x, let's see, I'll distribute that x in. So that'll be x to the 4th minus 3x cubed. And then I'll go ahead and use the difference of two squares on this, because again they are conjugates, the plus and the minus. So that'll be x squared minus I squared. And as a reminder, I squared is equal to negative 1. So this is x to the 4th minus 3x cubed times x squared plus 1. Now going ahead and multiplying that out using FOIL, we'll get x to the 6th minus 3x to the 5th plus x to the 4th minus 3x squared. And as a reminder, if you need any extra worksheets on doing FOIL, please let me know. So there we go, that was part A. We found a polynomial with the certain multiplicities required, and we're done with that part. Now we're going to sketch a possible graph of this polynomial. So for sketching a graph, when we have these complex values, we can't actually graph those numbers on the real number line. So we're just going to be graphing our zeros of 0 and 3. Because we had a 0, 3 and a 0, 0. Let me highlight those again. There we go. Let's go ahead and graph those. So we have a 0 at 0, 0, right there. And then we're going to have 1, 2, and 3. It happens there. So again, we know it's crossing here. Now let's take a look at the multiplicity. If there's a multiplicity of 1, it's just going to cross through. Even multiplicity, again, it bounces. An odd multiplicity, it curves. So 0 had a multiplicity of 3, which means we're going to be curving for 0. But which way? Let's see. Multiplicity of 3. And what did 3 had? 3 had a multiplicity of 1. So multiplicity of 1 is going to either be straight up or down through the axis. And multiplicity of 3, again, it's an odd multiplicity, so it's going to curve either up or curve down. How do we know which one to use? Well, again, let's take a look at our polynomial. Let's first figure out what the end behavior is supposed to look like. There's a positive number up front, and it's an even degree. So because an even degree and a positive coefficient, our end behavior is going to look like this. So end behavior is going to be heading upwards. So because of that, we know it's heading upwards here, and it has to head upwards here. And we just have to fill in the rest of this. So crossing through 0, we know it's going to do a small curving based on its multiplicity of 3. So we'll show that on the graph. It's not just going to go straight through. So to show that on the graph, let's just rewrite this a little bit to show the curve. And again, it's just a sketch. So let's see, it'll curve a little like that maybe. Just so a small curve at that point. And then it has to come back up to hit through 3. And because it's a multiplicity 1, it's just going to be straight through, so no curve. And on through. And there we go. So again, because 0 had multiplicity 3, we knew it had to have a curving to it, based on our definition above. And the way it curved, again, was based on our end behavior. And then for the 0 of 3, we knew it was going to be straight, based on its multiplicity of just being 1. All right, so that is that for the graphing. Now, lastly, let's take a look at another theorem, the boundedness theorem. So let p of x be a polynomial of degree n greater than or equal to 1 with a positive leading coefficient. Suppose p of x is divided synthetically by x minus c. If our c value is greater than 0 and the bottom row is non-negative, what does that mean? Basically 0 or greater, because remember, oopsie, the numbers. 0 is not actually a negative or a positive number, so when we're saying non-negative, we're including positives and 0. So when we find that out, then there's no 0 greater than c, and we call c an upper bound. If the c value we're dividing by and the bottom row alternates in sign between positive and negative, where 0 can be considered as either positive or negative, then there is no 0 less than c. And we would call c a lower bound. So for example 5, we have p of x equals 2x cubed plus x squared minus 13x plus 6. First, we have to list all the possible rational zeros of p of x. So again, to find all the possible rational zeros, first we want to find p and q. So p is going to be this value, and q is going to be that value. Okay, so we have p is 6, and the factors of p are going to be 1, 2, 3, and 6. Then for q, the factors of q are going to be from 2. Well, factors of 2 are just going to be 1 and 2. So let's find p and q. Again, we're doing positive and negatives, p divided by q. So writing those out, again, I'm just going to start with 1 and divide it by each of these. Then I'll do 2 again and divide it by each of these. So writing that out, let's see, we'll get 1, a half, 2, 3, 3 halves, and then 6. All right, so those are the options we have. If I wanted to write these in ascending powers to see what I'm looking at, I can go ahead and do that. Remember, we have the positive and negatives for each version. I could go ahead and reorder this as, let's see, negative 6, negative 3, negative 2, negative 1.5, negative 0.5, again just from the fractions, and then negative 1, 0.5, oh, positive 1, 0.5, positive 1.5, 2, 3, and 6. Again, these are all the possible zeros. It's not saying these are all the zeros, but these are the possible ones. So for B, we want to show that there is no 0 greater than 3. How can we show that there's no 0 greater than 3? Well, again, we'll do synthetic division, and if all of our bottom row is non-negative, we know it's an upper bound. Let's go ahead and do that. So again, synthetic division with 3. I'm using my polynomial from above. 2, 1, 13, negative 13, and 6. Again, feel free to pause the video and try this by yourself, and then check in with me. So that will be 2. Then 3 times 2 is 6. Adding those is 7. 3 times 7 is going to be 21. Adding those, we'll get 18. 3 times 18 is 54. Adding those, we'll get 60. So take a look at the signs. These are all non-negative. So if they're all non-negative, what do we know? We know 3 is an upper bound, which means anything bigger than 3 is not going to be a 0. So we can say goodbye to 6. That's not going to be a 0. 1 down, but better than all of them. Now let's go ahead and test negative 4. Is this going to be a lower bound? Well, let's see again using the same numbers for our polynomial. Let's go ahead and do the synthetic division. Alrighty, bringing down that 2. Negative 4 times 2 is going to be negative 8. Adding those is negative 7. Then negative 4 times negative 7 is going to give me 28, a positive 28. Adding those gives me 15. And again, multiplying the negative 4 to the 15 would give me negative 60. And adding those would give me a negative 54. So let's take a look at these signs. We have a positive, negative, positive, negative. Aha! They're alternating signs. And like my definition said, if they're alternating in sign, C is going to be a lower bound, which means negative 4 is a lower bound. So the numbers alternate in sign. So negative 4 is an upper bound, or a lower bound. Alrighty. So since negative 4 is a lower bound, we know that anything smaller than negative 4 would not be a possible 0, which knocks out negative 6. Alright, so for D, what are we doing for D? Oh, that was C. For D, find all zeros and write the polynomial in factored form. Okay, so this requires some guessing and checking because we still have all of these zeros to think from. Let's see. So, and how would we know if there's 0? We'll know if there's a 0 if this end number here when we do the synthetic division is a 0. Again, so there's no remainder. So I'm going to go ahead and just pick a random 0 to start with and, hope that it'll give me a 0. Let's see. I'll go ahead, we're working on D, and I'll start with negative 3 and do some synthetic division. If it gives me a remainder of 0, I know I can start factoring. So again, just using our polynomial as we have before. That's going to be 2. Negative 3 times 2 is negative 6. Adding those, negative 5. Negative 3 times negative 5, positive 15. Adding those two, we get a 2, and then negative 3 times 2 is, aha, negative 6. We end up with a remainder of 0. So we know negative 3 is a 0. Awesome. How would we know if something was not a 0? Well, let's try negative 1. Again, from my possible zeros. 2, 1, negative 13, and 6. We could bring down that 2, and that'd be 2. 2 times negative 1 is negative 2. Adding those is negative 1. Negative 1 times negative 1 is positive 1. Adding the 13 and the 1, we get a negative 12. 1 times negative 12 is going to be positive 12. And then adding those together, that would give me 18. Which, a remainder of 18, again, that's not a 0, which means this is not a 0. So that's how you would know if something's not a 0. But thankfully, the negative 3 is a 0. So we'll go ahead and keep working with the negative 3. So I know my function, p of x, is going to factor into x plus 3. Again, remember, we take the opposite to get that. From when we're solving a 0 to get that negative 3, just as a reminder. And then it's going to factor into these with starting at x squared, because again, it's going to be the lower degree. So we'll have 2x squared minus 5x plus 2. It factors into that. So now, you could go ahead and try doing another long division and seeing something else as a 0. But before we do that, let's ask ourselves, can we factor this trinomial? If we can't, we'd have to pick another random 0 and again test it again to see if we could factor it. But you know what? That does factor. So that is going to factor into the binomial 2x minus 1 and x minus 2. So again, if this had not factored, we'd have to go through the long division process again by picking another random 0 from our list of possible zeros. Plug it in and see if we end up with a remainder of 0. But thankfully, it factored, and we end up with the factored form. So we have the factored form, and lastly, we need to just write out all the zeros. So the zeros are, well, we know it's negative 3. And then let's find the other zeros. So we know each of these need to be set to 0 to solve my 0. So we get x equals a half, x equals 2, and again, we already knew x is negative 3. So again, these are all my possible zeros. Not all my possible zeros. Those are my zeros. And let's check. Were they in our possible zeros? Yep, there's the 2. There's the positive half. And there's that negative 3. So again, they all were from the possible zeros. But we know these are the ones because we factored them and we came from the long division. So my zeros are negative 3, positive half, and 2. Alrighty, and that is it for this video. Again, if you have any questions on using FOIL for multiplying out binomials or just factoring trinomials, please just send me an email and I'll give you a worksheet to practice those with. Other than that, have a good day.